Thank you. I did. Could you just check on YouTube? Because are you able to hear me? It might be a lag. Yeah, yeah. Should we- Just speak. Yeah. Okay. Okay. Sorry for the delay, but welcome you all to our preliminary design review. This is our second milestone for NASA Lunabotics Challenge 2026. Our first milestone was the system design review, which was scheduled last semester on December 7th. And based on system design review, we got a lot of feedback on which design to go forward with, because we had proposed two major designs in order to, like for our robot to be built on. Special thanks to our corporate sponsor, first and only corporate sponsor, Phil Wright, for their monetary and technical sponsor assistantship and sponsorship. So I just want to briefly introduce the Lunabotics Challenge. Every year, NASA organizes Lunabotics Challenge 2020. This year it's 2026. Organized in May. It's a 2-semester long project which starts in fall semesters and then continues till spring semesters. This year, the dates are around the commencement ceremony, like around 13th and 14th of May is when the competition will begin. The Robotics Challenge is basically for students to develop a robot which is capable to excavate and deposit BP1 regolith, which is a lunar simulant, lunar soil, basically. And in order for teams to win, you need to be energy efficient, fully autonomous. You need to make sure you're not hitting any obstacles, or your robot basically performs all the functions which it necessarily needs to. Introducing our team, I'm Sadeep. As I said, I'm the team lead. We have Sakshin Nasan, who is the drivetrain lead, Arnav, who is telemetry lead, Shaurya, who is navigation lead, Amit, who is AI and perception lead, Vance as electrical design lead, Nishad as mechanical design lead, Shruti as documentation lead, and Tia as our media manager. So, our first is project description, which I briefly introduced you about, is to create an autonomous robot capable of excavating, transporting, and depositing lunar regolith. When do we usually? This project started around in September, and since then we've had a lot of, including the first kickoff meeting, but other than that, a lot of irregular meetings here and there. But then we finalized this semester that we will meet every Friday at 7 p.m. on campus, and ECE teams usually have been meeting since last semester on Saturdays. Our project advisor is Dr. Yanfi Liu, and she's our official faculty advisor who is on the NASA record also. So this is just like, what do we know about the project and what do we have until now. Our need is to basically comply with the robotics rules, efficient excavation of BP1, reliable transport and deposition. Our major priority is following a fully autonomous cycle, like going for the maximum points. But our backup is we obviously have a backup, which is a semi-autonomous operation, which is kind of our alternative solution, and also fully manual, which we can control with an Xbox controller. That's what we're planning right now. Our major functional requirements would be excavation, transportation, deposition, navigation, and automation. Our failure modes are robot fails to excavate regulate, one of the biggest failure modes which ME team had to work on. Robot becomes stuck in an arena. There are a lot of craters in the arena which the robot might get stuck into, so that's one of the failure modes. And regolith jams in the transport system. Regolith is very like it's it flows. It's like similar to flour, like rice flour or like plain flour, because it whenever you're excavating, depositing, or transporting, there is a good chance that there is dust release, and that might jam the mechanical and electrical systems which we have. Our given requirements, the robot must fit within 150 centimeters into 75 centimeters into 75 centimeters. This is the max. These are the maximum dimensions, and these are what we are going for. The robot must not exceed 80 kilograms. Robot must have an accessible e-stop button, which is the main functional requirement. Robot must use allowable sensors for navigation. No GPS and ultrasonic sound is allowed, and which is our kind of a physical solution, alternative solution. Right now we are at whatever we have right now is batteries and BMS, which is $118, computing and sensors, which includes a Jetson Orin Nano, sponsored through ECE department. Software subscriptions around $350, which is sponsored through Dr. Elfayoumi's sponsorship. And a domain and miscellaneous is we are trying to create a custom domain for our website, which we have currently under development, but we are still in the process of getting copyrights as like allocated through the university for us, since we are using the university branding. The standards we are following are Lunabotics rules, OSHA electrical safety standards, IEC, which is again IEC 60241, which is mentioned in the rule book, and obviously the IEEE robotics and automation standards, which are renowned for their robotic practices. Safety concerns, there's very big chance of electrical system failure, as you know, something might heat up, burn down the entire thing. Very good chance, but obviously we will make sure it doesn't happen. Moving mechanical systems, excavation, deposition, and drive mechanisms may pose risks, because what if it just the motors don't work properly, or like the excavation system doesn't work properly, or the deposition system doesn't work properly? Might cause an issue. Loss of control or collision. Since we are focusing on fully autonomous mode, we got to know from Purdue main campus that not a single team has achieved 100% autonomous mode. There is some chance that the teams might fail autonomy. But our goal right now is prioritize 100% autonomy so that we go for maximum points. But there's a good chance that it might fail, so that's one of the concerns we are looking for. And then the basic responsibilities are electrical safety, mechanical safety, dust mitigation, and safe operation, which are followed all across the industry. What life cycle related steps? It should be producible. This competition occurs every year, so whatever we have, like from this year, next year also the team if the resources are not provided, the team would be able to produce the same thing. Scalable. We will show you a proof of live, the basic one which we have on the mechanical side. So if we need to create a proof of life, it can be scaled down, it can be scaled bigger. Basically, our robot is a very modular, is based on a very modular design. Portable, we need to transport a robot from Fort Wayne to Florida in May. So we need to make sure it can be carried. It's 99% sure that we're going to carry it through road, but in order for it to go in a car or a van, it needs to be in that perfect size. Reliable, obviously, to perform all its tasks, it has to be reliable, maintainable. Something fails, something goes down, or like not performing well, we need to have control. We need to do the maintenance. Recyclable, obviously one of the biggest things. Disposable, one of the clear things mentioned in the rule book is the robot should be easily disposed after the challenge is completed, and we need to tell them how we are going to do it. Are we disassembling it, or are we going to reuse it next semester, or is it just going to be as a display piece in your university? And remanufacturable, because we are doing all the custom parts. We should be able to remanufacture whatever we have had before. So our main things, what we are going for would be the functional requirements, what the robot needs to perform. Is work autonomously to excavate and deposit regulate from one side of the arena to another. Now, what are the measures which we are looking forward to and which we think are the most important ones? Is maximize regolith collection. Regolith collection is like, if we maximize regolith collection when we are depositing, we have a higher size berm. A berm is like a structure on which the NASA space shuttles or landing vehicles will land on. So it needs to be it needs to be of a specific size and volume. So we need to make sure that every run of excavation, sorry, it needs to have 20 kgs. Minimize mass. So if in order for the robot to function well, if it's of a lower size or lower mass, we can add more regolith to it, and once more regolith is added, it can achieve that maximum mass at which the motors are rated, like the torque at which the motors are rated, so that any mechanical part or any electrical part does not overwhelm with the mass. Maximize autonomy. That's our major goal. That's one of the biggest goals we have. Minimum points which we can get for autonomy is 420 points. That is one autonomy cycle. That includes all basic mistakes made and then cut off. But the highest we could go is for autonomy is 600 points, and whoever gets those 600 points obviously wins the competition. One of the main requirements mentioned in the rulebook are minimized bandwidth. They need to have a minimum of 4 Mbps or 400 kbps bandwidth. We will try to make sure it goes until there or a bit lower. Maximize detection accuracy. Detection is basically for berms, if there is any wall, any obstacle, or any sort of unnecessary object in the arena. It's the robot's responsibility to detect it accurately and then move away from it. Then our major use cases would be excavation, deposition, and traversing. So this flowchart will explain how the robot is going to traverse through BP1 arena. Basically, start with initialization of sensors, then you go through localization. Localization is basically the robot knows that where it is standing in the arena. Then pathfinding initiates and mapping begins, so that it knows where to go, either to excavation site or to deposition site. Then the drivetrain starts, that is, it starts moving, and it locates the zones where it needs to go and stop in the designated zones. Our mechanical system is basically responsible for excavation and deposition. So mechanical system initialization is when the motors are initialized. Then chassis positioning obviously happens through localization and mapping. Excavation mechanism deployment. So excavation system starts collecting it. Then once it starts collecting, it will store it in a container, and then obviously locate the zones, and then it will move to those zones. So I'll ask the ME team to take over from.
So one of the biggest problems that we had to overcome as a team was deciding between both of these ideas, which was something we had discussed very detailed in the system design review. So the first idea that we had was the internal loader, which is essentially a design that has a scoop in the middle of the robot chassis that picks it up kind of like a swing motion with a predefined path, so that it can excavate and deposit sand with just one predefined motion. And the second idea that we were considering was the bucket ladder, which uses a conveyor belt that has multiple buckets on it so that it scoops sand and it deposits that into a storage container, which further drives to the area and deposits sand over there. We ended up going with the bucket ladder as opposed to how we were leaning towards the first option in the system design review. We ended up choosing the bucket ladder design for multiple reasons, budget considerations, based on how much experience the team has overall. This design is also the most used design in the competition overall. So there's multiple open source designs. There's multiple researchers that is there for this design. So going forward, considering that we're a new team, we took the decision to go for a design that's been used so that we can focus more on autonomy as well. Since this is a design that's been used so much, we thought that focusing on autonomy would be a huge boost for us, or at least help us, be us different from other teams. Obviously, the most useful parts of this design is that it's unbelievably easy. Yep.
Do you have to dump the payload?
Yeah. So we were thinking other teams use a lot of different methods. Some of them use a conveyor belt in the storage as well as a way of deposition. But we were thinking that we would dump it mechanically from.
That's the hydraulic.
Yeah, so this would be the conveyor belt that moves down, it'll rotate and it'll deposit sand into the storage, which will then drive to the deposition area and then deposit sand. Obviously, one of the biggest considerations for this design would be the amount of dust that it throws up, as one of the points that NASA does consider is how much sand gets thrown up overall, as well as how much sand gets on the robot. And considering it's an entire room full of sand, it's going to be hard for us to, get over that wall. And there's also a high number of moving parts, which means that, there's quite a few room for failure, but we can accommodate that. So our drivetrain follows a skid steer system, which means that when turning, one side moves in one direction and the other side of the drivetrain moves in the opposite direction to allow for the robot to turn properly. And we also are going with the rear wheel drive, so the motors are going to be placed at the back of the robot, as research says that that's the best way to traverse through sand. As of now, based on based on the CAD models that we've made, we have an estimation of about 23 to 28 kgs for the mass of just the drivetrain, and most likely we will be using aluminum alloy, some kind of lightweight aluminum alloy to follow the drivetrain. The wheels, I think you can pass that on. So we have a scale down that's scale 1/5 of the size of how our actual wheel will look. And we were thinking that rather than using metal for the wheels, we would use plastic, as that's makes it lighter weight.
You may I ask them? So while he's logging back in, have you calculated how wide and how deep these wheels need to be?
Yeah. So I think in terms of width, it's about I think 30 centimeters in diameter and about like 10 in width, if I'm not wrong.
This is scaled down to 1/5.
Yeah.
Yeah.
So
The original would be 5 times bigger than this.
My guess is you might have to play with the depth.
Yeah, that's something we'd have to figure out in testing, I guess.
Hit HDMI. Stop moving that mouse.
Where?
Don't move the mouse.
Oh, this one?
Yeah. That mouse is not connected. Yeah, don't move that mouse.
Oh, okay. So for our further into detail about the excavation system. So the bucket ladder, as we mentioned before, would descend down into the sand. It'll rotate, and the buckets would then collect sand and deposit into the storage. We are planning on using some kind of cover or a funnel to allow less sand to be thrown up and dispersed everywhere, and so that sand flows directly into our storage. As based on our research, one of the biggest problems that teams have is that either a lot of dust gets collected when collected, a lot of dust gets thrown up when collecting the sand, and a lot of dust gets thrown up when getting the sand into the storage. So we're also going to be using a slower motion compared to other teams, so that we get sand smoothly without throwing up as much dust as possible, and while collecting as much as we can. We were also planning on using a zigzag type motion, so it'll be one bucket over here, over here, over here, so that we can accommodate more sand rather than having too much weight onto one big bucket in a specific area. As mentioned before, some of the considerations we'd have with that would be dust exposure, either to too many moving components, or the bucket spacing is slightly off, or the speed of how the bucket ladder rotates. And that's something we'll go way further into when we're testing the robot. And we have 2 months for testing, so I think we're gonna figure out a lot then. We were also planning on using pulley type system, so there'll be 3 gears with chains attached to all of them, and this entire module would also be connected to an actuator, which allows it to move up and down. Oh, my bad.
If you all think of having like a flap cover to those buckets, that perhaps the flap, the way it's positioned is would be open while it's loading the sand, and once it loads and starts moving up, that flap will just drop, covering it, reduce the amount.
You mean the buckets on the conveyor belt?
What's on the conveyor?
I don't think we'd really need a cover for that, because the way the motion goes, I think all the sand will get deposited and then it'll stop. So I'm pretty sure that by the time the robot starts moving again after excavation, there'll be no sand remaining in the buckets. So I don't think, I mean, that's a good idea, but right now we haven't considered that. So for the key mechanical system we're using for the deposition is that both the storage and the conveyor belt move together. So as the conveyor belt descends downwards into the sand to rotate and pick up sand, this part of the storage would pivot downwards as well. And so that one, sand gets more easily into the storage, and also furthermore, when we are going into deposition, so when the robot finally travels all the way to the zone where it has to deposit the sand, we'll have the same mechanism move further up, and we have a pivot over here, so that this entire storage system kind of pivots upward and sand dumps downward. And the entire system moves in tandem, so that we once again have less moving parts and it all flows together. Then
Suggest one thing, I'm not sure if you consider that or not. But what if that container from the storage in the back is somewhat tilted, so it is lower from the back than it is from the
we
front?
were going to do that, yeah. So we already, last time we discussed, yeah, the inside as well is going to kind of be inclined, so that,
It's very inclined from the front, but declined from the
yeah.
back. And then
So-
all what you need, so rather
Like
than
that.
lifting it, yeah, exactly. You just need to have a door at the back that fits with
Yeah.
the opposite.
Yeah,
That's what
and then there is a good chance that the regulator might not dump properly, so we have like small vibrators on the tank. So it just vibrates a little much and then it just slips.
Because as we mentioned before, the BP1 regolith has a consistency of flour, so we can't depend fully on just gravity, as there's a chance it could definitely just stay on. And yeah, I think I forgot a point, which is that the drivetrain as well is going to be moving on a pulley system, so that will work in that way as well. Then, yep.
Pulley system, like John Deere makes combines, right? So they're dealing with dust. How do they design their and also if you look at the combines, they have this kind of rotational pickup, right? How do they isolate the mechanical drive so that dust doesn't interfere with it?
My guess, based on the research we've done, would be the one thing is the speed of the conveyor belt along with the exact way it picks up. So main campus, the team on main campus, rather than having buckets, they just have like bars like this just there, and that picks up sand, and they just continuously move that, and it throws up a lot of sand. So as we said, the easiest way for us would be going in a slow, precise motion, so that it picks it up as required. It drops it as required, nothing too fast, so that it doesn't throw up to sand or create too big of a hole for the robot to drive over.
I think that your major concern, based on what I am understanding, is when it's excavating, is how do you prevent the dust
Well, I'm
formation?
thinking dust inside those.
Oh yeah, so I mean, if you go to the slide before, yeah, if you see that the thing is covered from each of the side, which is going on the pulley. So
So the entire gear system on the inside is going to be covered completely.
yeah, and there's going to be a cover over the buckets as well, so that even if it loses any light with it, it doesn't fall down. It will stay within that zone. Only the bottommost bucket, which is going to pick up the sand, is going to be exposed.
Okay, great.
Yeah.
That way, that's also why as the sand goes from those specific buckets into the storage, we'd have a cover that guides it, a pipe, a funnel, something like that, so that it goes directly into the storage, nowhere else, doesn't go all over the place. Yeah. Electrical thing.
So for the electrical system, let's start with where it's gonna get power from. So the battery will be powering the entire robot. There will be an e-stop there because according to Lunabotic rules, we need to have an e-stop that can be pressed whenever we need to enter the arena to stop it. And it should be exposed so for easy pressing. Then so power will go to the PDB, the power distribution board, because we're dealing the battery right now is what
22.2.
yeah 22.
22.2.
Yeah. So we have motors and microcontrollers which operate on very different voltages. So the power distribution board will be scaling down the voltages according to which application you'll go to. So then power will go to the Jetson, which is getting feedback from situational cameras, the depth cameras, LiDAR, and UWB tag. The Wi-Fi is there as a way to control the robot if we ever need to go to manual mode, if autonomous mode fails. Then the Jetson takes all the information from the sensors and it will be deciding navigation, pathfinding, and all that. And based off of what it decides, it'll then send those information to the teensy, which will drive the motors. Send the PWM signals to the motor drivers, which will allow the motors to drive or excavate, or if we have any other like applications like linear actuators to lift deposition or stuff like that. And then we also have the WB anchors on the outside of the arena, or like the sides of the arena, as a way of a secondary localization method. So that's right now the current electrical system. It might change depending on if we need to add more components, or we are thinking of possibly getting rid of the teensy and controlling the motors by the Jetson itself. So
What would what input would it take this teensy and what would the output?
So the input it'll get is from the Jetson. It'll be like a vector.
Yeah.
Like
That's a speed vector, right?
speed vector, right?
Sure. The like input output from the Jetson would be a speed vector, right? Yeah.
Oh yeah, that'll be a speed vector. To the teensy will calculate how much it'll need to move the motors, and then it'll send a PWM signal to the motor drivers, which will then enable the motors to drive. So that's
So I can see why you would want the Jetson to do that if you
Yeah.
Yeah.
Just bypass the TNC
get
completely.
rid of it.
Mhm.
Also with the speed vector, it will change in real time because it might pick up too much sand. So according to the weight of the sand it has picked up, it might slower the speed by a tad bit.
Yeah.
Yeah.
The main reason of the TNC is that it has PWM signals, which will be that's our current method of driving the motor drivers. But we might be getting motors that you don't need to send PWM signals and can be directly connected to the Jetson, which will completely eliminate the need of the TNC.
I mean, the voltage in the GPIO pins of the Jetson should be enough to convey that signal to the to the motor driver. So it shouldn't be that complicated.
Any other questions about the?
Oh, that's great.
Yeah.
And what, so mission control center is also something you're designing?
Yes, mission control center. So by rules, we are supposed to always have connection with the robot. If we lose connection, it is automatic, like forfeit, essentially.
Yes.
So this is why the mission control center is very important that it has connection to the bot. But we we probably won't need to use it because we plan on having the bot be completely autonomous. So mission control center is basically a fail-safe if we need to move to semi-autonomous or manual mode.
I think the only thing which we didn't include because that's not the priority right now is the data logger, which will tell like how much power each of them is, which is also a main requirement. It should be commercial off the shelf COTS, so that the judge is going to review how much power each component or the robot is consuming, or like voltages and other things which they have in their gradebook.
There is also technically another thing we might add. This is a senior design. If
Yeah.
for the spring senior design, if it gets accepted, that we'll have wheel encoders on the motors, which will also be connected then to the Jetson. That way we can figure out if there's slippage of the wheels, and we could change pathfinding and navigation according to that.
Just as a safety mechanism.
Yeah.
Will you need both LiDAR and camera?
Okay, so because of dust pickup, like camera would be good by itself, but the problem is craters are the same color as the sand, so there might be issues with that, shadows, glare. There's multiple different like obstacles that can interfere with the camera. And so that's where the LiDAR comes in. But then the problem with just using a LiDAR system is because of dust pickup, it might interfere with it, and vision system would be more reliable in the event that there's too much dust that the LiDAR is unreliable. So that's why we need two.
So the challenge is to know which signal to use when.
Yes, we will be talking about it later, but we are thinking of implementing a system using the cameras, LiDAR, and then wheel geometry all together as a way of like mapping and localization based off of this paper we found called Ground Fusion Plus Plus, which has a really good way of increasing and decreasing dependency on each sensor depending on what the situation is. So, yeah.
Okay. You have the bathroom?
No. I mean, okay, so this is where we'll battery we will use, which is the 7 series. Nominal voltage will be like 24 volts. So we're gonna have 2 of them in parallel, and not daisy chained explicitly because of the rule book, and also it's not particularly safe. And then this is our BMS we were using. It's rated for up to 60 amps. So based on the current actuators and motors we are going to be using, this should be the peak load of everything running at once with a 20% buffer. So the BMS should be more enough, and then as discussed earlier, the e-stop and data logger are required. So this is just the power source for it all. Okay, so I have the power distribution board split into two parts, what I call the LVS and HVS, low voltage system and high voltage system. So kind of as we discussed earlier, we have the microcontrollers as well as the sensors to power, but then also the drivetrain. So I settled with buck converters because it is the best way and most efficient way to step down the voltage or step up in certain cases for the high voltage system, a buck boost that would be. And so we chose the in this case an IC which I'll discuss more in a second, but yeah, effectively the requirements are, it's just for the low voltage system is no more than 4 amps out, and then the 3.3 volts for the sensors, and then 5 volts for the Jessen. It might need to be 12, but 5 should be sufficient. If 12 is needed, all we have to do is the lower feedback resistor in the bottom right. So look, it's both this 5 volt and 3 volt system, 3.3 volt system. You just adjust that resistor. That's effectively according to the data sheet. So yeah, the TPS 5450 is the IC we'll use. Technically, the 5430 would be fine, but there's no reason not to go with the 5450, which the only difference is 3 amp, 5 amp peak load. So yeah. And then, so it supports up to 5 amps. So this will be more than enough for our low voltage system for sensors and microcontrollers. So okay, so this is the high voltage system. I'll explain it more in a second, but here's a schematic. The only weird thing I did here, just so it's a little bit more viewable, is this little arrow thing. So it has 12 capacitors as a bank to reduce the ripple. So that it's flatter, and yeah, so I'll explain more here in a second. So we're just going to be using the LM5122, which took a lot of decision making, a lot of comparisons to other ICs to settle with this one. During the last review, I was going to use the 5170Q, but this one was chosen instead because its behavior is more predictable, and the other one, at least there was no really great way, or at least described in the data sheet, to have the same capacitor bank. So that's great, and yeah, so we wanted that so the converter doesn't oscillate and it's more reliable. So yeah, 12 amps out. So for this is just assuming, so the whole system, we will need multiple of the high voltage system for each motor, or depending on which motor we go for. This is assuming a 36 volt motor, and it was 350 watts. The one I was referencing, at least. This can be very easily adjustable, and it was at, I think, like 9.5 amps. So again, I try to have a 20% buffer for the max current out. So that's why we settled with 12 amps here. And then the shielded inductors, after doing my simulations, that using that opposed to non-shielded conductors, is like a 1% efficiency gain. There's really no point to not do it because the price is negligible. So yeah, and then then according to my simulations, this is the efficiencies. I was actually very surprised and happy with this efficiency rate. So continuing, so far, getting the individual models for the for the PCB is like some are not on the software. I'm using Altium, but that's effectively what it'll look like for the high voltage system. So we'll have bus bars, so that multiple devices or multiple motors, whatever, can connect to that for power, and that'll be external. And then 8 gauge stranded wire, stranded for obvious reasons because you know, the flexibility and the high current that might go through it. And then 8 gauge is consistent with that of the battery pack that we will be using, and it should be more than sufficient, and it should not get very warm at all. So it's a little overkill, but I think that's fine. Then for dust resistance, which is the acrylic conformal coat. So there's lots of conformal coats we could be using. So typically, you know, always polymer. So acrylic was chosen because it's very easy. Well, firstly, it's quite inexpensive, but secondly, because it's very easy to remove, and if something were to go wrong, it would not be. We wouldn't have to print out a full new PCB, but it's still plenty durable for our needs, and would mitigate most issues of dust resistance. On the note of dust resistance, we will have a chassis, so as described here, for the PCBs, and it'll house also the microcontrollers and everything, and what was I saying? So we'll have a chassis for the housing, and we'll have it sealed around the edges where you open it up, so that it also there's no chance of dust resistance, because not all the components, for example the Jetson, will not be conformal coated, obviously, and so we'll arrange them accordingly. But that should be plain enough. The conformal coat is just to really make sure. It's most important for it to be on the power distribution board, because, yeah. And then, yeah, sure.
How many layer board is that?
It just, I think it was 3, or sorry. I mean, so it was just dual-sided, just two-sided.
Two-sided?
Yeah, two-sided. And then there's the copper, you know, pad for the ground.
We're working on purchasing a machine that will print boards, 2-layer boards. Top
Yeah.
and bottom.
Yeah.
We'll also do reflow of surface mount device. So in the queue, so you're welcome to use that. That'll be in the lab also.
Okay.
Yeah, we think we were talking about that a little bit, so.
And what I found out is that they have their own, it's proprietary ink, but the ink is conductive ink. So you can print the circuit board layers, and it does two-sided. So
Yeah.
I'm really excited about that. That'd be
That'd be awesome.
Or you can change it. So.
Yeah, that'd be awesome. Right now we're kind of planning, just in case, you know, to make it so we don't really have to change it. But if that's available, that'll be great, and we definitely.
But where are you building all this?
We have.
So I mean, we have like locations we can do it in, but we don't have one definitive place really designated for building.
We have,
Some place that can have dust, I guess.
yeah. Right now, for building the bot, we have 2 rooms, but they're very small. One is
ET120.
ET120 and then ET331.
Okay.
but both also lack in tools mechanically wise, so it'd be hard to build that, and they're also again very small. And then for the dust pit, I think
Dust pit, ETCS told us that they will be making a dust pit. We're not sure where, but they said they should be able to get it done by March. It's going to be an outdoor dust pit with volleyball court sand or like beach sand, and with a covering on top so rain, snow, or wind won't affect it much.
Maybe you guys can show me the labs, because, and what you need tooling wise.
Okay.
Because we could possibly buy, well, we just talked. But I think probably putting the dirt inside of buildings not a good idea.
Yeah, that's
yeah, we're not doing that.
yeah. I mean, the only reason
It's
we
not
had asked,
person, I guess, but
we asked for a possibility for an indoor one is because of we can't do an outdoor testing if the weather is bad. So that's the only reason. And we don't want the robot to get affected through anything.
well, you know, the guys that are over in, that are building the boat,
They are in ERC garage.
it's not heated, but it's at least indoors.
Indoors, yeah.
Yeah.
Something in those sorts, but at least which outdoor factors should not affect the robot or the pit at all.
Yeah, so it'd be better if you had the dust pit indoors.
Yeah.
Even if not heated.
Yeah.
Well,
So even any parking garages would have worked, like a corner of a parking garage, because at least that would also save it from majority of the snow and rain.
I don't know who to ask on that, but maybe we talk to Dr. Long about it. too. Since we have the crane competition boat in that ERC. So it's a huge space.
Yeah, maybe just one corner. We just need a dimension of 5 feet by 5 feet by 4 feet. Like it's just height.
That's it.
Yeah, we just need to test it.
Yeah, we just have to see if it excavates.
We need to
onto
see how it moves on like a sand type ground.
Yeah.
How big is the arena?
It says in the rule book.
Is that like 10 by 13 meters?
I think that sounds about right. Yeah, around 10 by
We'll
30.
just pull up after the presentation.
Yeah.
Yeah, we can pull up the rule book to verify that for.
Because we want to build one to the exact spec that they're using.
Well, that's
I don't-
what
no-
I'd love to, but
No one even has that. I mean, that would
I know what the problem
Well,
is.
that's an
it would definitely be, yeah. Seriously.
But actually, right now the rulebook itself is in a draft. The
Oh.
NASA has not released a full complete.
Rule.
So yeah, because of that, we do not have the exact dimensions of the arena, and we have a rough estimate what they're going to use based off of last year's. But yeah, until we get that, I
What's
think,
your roughest?
again,
15 meters by 15. 15 by 12 or something.
yeah,
Somewhere around there. Again, we'll confirm it once we're done through the rule book. But
Yeah.
yeah,
I mean,
Purdue main campus
we
has
just
like
asked
what,
for
a
bare
quarter,
minimum
a
because
third.
I
Do you
didn't
have,
know if they
like,
would
what?
like approve something if we asked for something big. I didn't know if anyone had like if the departments have money to build that much, because everyone has been telling us there's a budget cut. That's why we were asking for the bare minimum we need to test
The
it.
dirt is cheap, right?
Yeah. Regolith is
Oh no, the actual special was a BP1.
BP1.
Yeah, that's very
That's
expensive.
$55
But
per kilogram, and a kilogram is about this much.
Yeah.
yeah,
Because
so
it is very dense.
so the alternatives for testing is so sand's the cheapest option. As we said multiple times here, cooking flour is very similar to the Regolith BP1. So that's really good, but mold issues
Cooking
with
flour
that.
will cause like mold.
Yeah, no, it costs a lot more.
My wife does love taking it.
Yeah, we did look into it.
You
25.
can get the wheat before they mill it.
Oh.
Yeah,
And it doesn't mold.
really.
That's how they survived in the 19th century. You wouldn't buy flour, you would buy
Yeah.
the grain itself, and then you would mill it when you needed to.
Yeah.
Anyway, but maybe we mix sand and something.
Yeah, but a lot of people do is they don't even do some sort of power. They just put in like a volleyball court, sand or something. That's what a lot of the universities do.
And then you could get 2x8s or something. and build
Yeah.
it.
Yeah, I mean that'd be great.
Yeah.
So
So like a flower garden. Have you seen those?
Yeah, the raised bed gardens. Yeah.
Yeah, they use like 2x8s, 2x10s.
Yeah.
Would that work?
Yeah,
That-
that will be more than
that will be
enough.
more than-
Yeah, that will be more than enough.
It's cheapest lumber.
We will technically try to kind of have to make a wall
Yeah,
for the LiDAR.
lidars. Yeah,
Just to,
like a
yeah.
glass wall we need.
I know, we could use plexiglass or some kind of.
Yeah, basic.
Yeah.
Just so that we know that it doesn't detect that. Or
So
like,
does the department have a budget for this at all?
No.
we were given only 500,000.
Yes.
So we needed him to work.
I mean, Dean gave us $1,000.
Oh, he did.
EC department gave us 500,
Okay.
but that's still bare minimum. I think we'll cover that like when we come to the budget part, but
Okay.
like we are at the bare minimum what which
Right
one
now,
we-
all the money is going towards the bot. We do not have any testing plays, tools. We were borrowing and all that. So
everything
Yeah.
is
Yeah, we're just kind of scraping by.
yeah.
It's 7 by 11. The area.
Oh,
okay.
7 meters by 11 meters for the actual area where the robot has to pick up.
Okay. And that's the spec.
yeah.
Unless they change it for the upcoming.
Yeah.
Yeah.
I mean, even 5 meters by 5 meters should do for us. Like,
Oh, that's-
yeah. Yeah.
So they sell lumber in 8 sections, so
Oh, then 8 by 8.
3 pieces by 35 feet. 3 by 4 would be close enough.
Oh yeah.
Okay.
It should be.
Okay. Yeah. All right.
Thank you.
Okay.
So, yeah, LiDAR sensor. This is very. We haven't fully decided on LiDARs because the spring senior design project will be doing that. But our basic LiDAR, what we're gonna have is we need it because if there's a wall or something, we need it to be able to detect. Because in the actual arena, they were using some translucent material as a way of separating the pits and all that, and that caused very big problems for bots that were just vision based and did not have a LiDAR system. So we have the LiDAR for that. We need to have about like 7 meters. The reason is because it's like you said, 11 by 7.
Yeah.
Yeah. So that'll fully cover the entire arena. We need it to be fast scanning, so more than 10 hertz. And it'll work simultaneously with the the camera systems. So it needs to scan a lot, and then we also needed to have basically preferably 360 view, but right now because of our limited budget, we're gonna be working with more lower quality LiDAR sensors, so like 180 probably degrees. And then in terms of dust protection, because dust kickup is what'll have the LiDAR fail, so we're gonna have probably some kind of covering that will 3D print around it and put on it. So these are the requirements. What we decided based off of these requirements was the RP LiDAR. So the RP LiDAR is a 2D LiDAR. And so we will be using it as, again, with the vision system. Preferably we'd like a 3D LiDAR, but because of like budget, we have to deal with 2D LiDAR. The 2D LiDAR, we are currently still deciding where to put it because the problem is we need the LiDAR as a way of helping sense the craters, rocks, and all that. So it'll be pretty low, but at the same time, if there's like pillars, walls, or some other obstacle that has more height to it, then it needs to be high. So that's why the 2D LiDAR has those like problems and fallbacks because of so we still haven't decided where on the robot we're gonna put it. preferably this is why we need the 3D. That way we can get like we don't have to worry about placement that much. It can scan everywhere, and we don't have and because right now for the 2D we might actually consider having it go up and down, but that will create that means we'll need to use a motor for that, and that'll increase increase power usage, which one of the things about the Lunabotics is trying to be power efficient. So, and then yeah, it is cheap. It's for a LiDAR, 80 to 100. And then it does have dust protection, so that's going to be really helpful because the most dust that gets picked up is during excavation, right? Yes. But I don't think we'll be using LiDAR during that, but it will be, the dust will be all over the LiDAR at that point. Hopefully, right now, as a mechanism to get rid of the dust, if there is buildup on the LiDAR sensor, is since the very vibration sensor we're going to be using, motor we're going to be using as a way to deposit, that'll be a good way to shake off the dust from the LiDAR. It's very interesting way of dealing with it, but again, that's what we have. And then we're going to be using UART as a way of communicating with the with the Jetson or Nano. And yeah, we are hopefully looking for a LiDAR that we can connect using USB, because it'll be like, while the Jetson or Nano is a microcontroller with GPIO ports, it's better used with USB interfacing and all that. So yeah, and then for so like the LiDAR, which helps with positioning of the bot in the field, UWB ultra wideband would be used as a way of basically triangulating the position of the robot and having it help with the localization that the vision system will be using. So the rule book says that we're allowed anchors in the field in the starting zone. So we were going to have 3 anchors, and these are going to be continuously transmitting a signal, and then we were originally going to have 1 sensor on here, but taking inspiration from the boat project senior design project, we figured if we were to use 2, we'd be able to tell which way the bot is facing. Because another thing that happens in the competition is the bot is placed in the starting zone, but we do not know which orientation they're going to put it in. So it could be facing the wall, it could be facing the arena. We don't know. And we're not allowed to detect the walls as a way of localizing the bot and figuring out which way. That is automatic disqualification. And we are technically allowed to use like QR codes or April tags as a way of localization, but that cuts points. So that's why, to avoid that, we're going to use UWB as a way of initializing its like location.
So is this the black, is that the?
A wall. That is the
boundary?
the boundary.
And so that's 7 meters by
Yep, by 11.
Yeah.
And so what's the blue?
Oh, that blue. I took a screenshot.
It's
from
just a small snapshot of one corner of the entire.
yeah.
So are you allowed to go inside blue also?
Oh yeah.
Oh, that's not
That's
actually
not
a zone. That's like something pointing to something else
Yeah.
on the photo.
Yeah.
It's just an arrow.
Yeah, the blue is actually just a way of telling the actual dimension of the entire thing, but in the actual map of the arena. But the green outline is the starting zone that we're doing. So yeah.
Yeah, and many, it's interesting that you're talking to the
Both
great
projects.
competition.
Yes.
Because I was thinking, the autonomous control is autonomous control.
Mm-hmm. So originally, yeah.
This is how it's set.
Oh, okay.
You can see from
So you do have a basic idea. I see. Okay. So that comes from their spec.
Yeah, yeah.
Spec.
But yeah, so before talking to about project, originally what we were going to do is just have one sensor on the middle or maybe slightly offset to the front of the bot, and then use the accelerometer and the IMU data as a way of figuring out where the front of the robot is. But that would have been very problematic and unreliable. And then if you were to use the cameras as a way of like localization, using the April tags, that would again cause loss of points. So yeah, having the two tags on the bot, one in front and one in the back, is a really good way that I'm happy that I talked to you about the project about, because that was a solution I would have not thought about. There is difference, obviously. They were using GPS, we are using UWB. And how it's gonna so GPS uses a global position, like a satellite, right? This, since it has to be a local system, what it's gonna do is the anchor is gonna talk to the tag, and they're gonna figure out the time of flight or how long it took for the communication to happen, and figure out distance based off of time of flight. And once once it figures that out, there is gonna be probably some error because UWB tags have an error rate of around 10 centimeters. We're hoping for less than that, and then
Time of light.
time of flight.
Flight.
So UWB is a type of radio communication, ultra wideband. So it's gonna be sending pulses essentially, and so yeah, it is
Same idea.
Tell the full form.
Yeah, so you're
Yeah.
calculating how long it takes to
yes.
transmit the signal, and sort of like radar.
Yes, and the problematic part is since this is there's no like synchronized clock, so you have to figure out when was the signal sent and all that data.
And
So
then you sync the clock.
how do you sync the clocks? So
Yeah.
right now we're using asynchronous positioning because like we're thinking of that, but synchronous would be necessary for like time of flight. So yeah, that's probably what we're gonna go with. So yeah, those are some problems we'll have to deal with, figure out.
You know, that was the first key in navigation to
Mhm.
determine longitude.
Yes.
They had to have synchronized clocks.
Yep. So, for the UWB board, we're going to use the Arduino Stella. This is actually surprisingly cheap for UWB, especially for real-time location, because when you're using the most common chip for UWB is the EWB 1000, which can take like 5 seconds to figure out the time of flight and the signal rate, and like basically trying to localize the bot. But since they're using the DCU 040, and that'll actually latency is 0.2 seconds, which is as close to real time we can get, and it'll reduce the need for having too much computation on vision systems for localization. And we do have to use a frequency range above 5 gigahertz because we cannot risk interfering with the Wi-Fi signal, because if it does, then if it loses connection with the MCC, we get disqualified. So we're looking to use the 8 gigahertz band. And then there is also the encoders that we're thinking of using, but that will be up to the senior design. And then the so what the senior design project will be, who will be helping us, is they'll be working with the LiDAR, UWB, the wheel encoders, and basically they'd be using that as a entire way of a non-GPS navigational subsystem for the bot. So that's what they will be helping.
So they're working on what?
If this is the project proposal for the spring 2026 senior design that we'll be using. They'll be
Implement a non-GPS indoor nav system for NASA.
yes.
Estimating position and heading in. So they have to know position and rotation.
Mm-hmm. So that's where the wheel encoders come in and the IMU data from camera or the Arduino Stellar.
So how does this project fit with you guys
It fits with us because
in terms of timing?
in terms of timing, so actually timeline. So we have to do a sense of bring up, directing, and just characterization, which will be more than enough to help get this done in time for the competition. And then we could continue basically fine tuning and refining it completely in the second semester and have a completely non-vision based system in case vision fails. So that's what it'll
I suggest that you guys on this project side define some sort of interface spec. How their work interfaces with you guys.
Yeah. So since thankfully, since I'm taking senior design right now and I'll be on that project, it'll we'll be discussing very closely on that.
But Deep knows kind of the interface diagram, you know, that we used in senior design 1. The system boundary.
System boundary.
That
I mean,
it
it's still in
defines interface.
process. Like since we don't know what is being covered in senior design or our thing, that's why we have the basic system architecture which we showed before.
So
But the idea is to define the blocks
Yeah,
and then what is passed across the interfaces.
we should have that by our CDR.
And
detailed one.
yeah.
so even the mechanical is an interface. So I mean that, you know, you might just say that there's a mechanical interface and then have a detailed design drawing to show how what they're doing mounts to your device. So I'm thinking we should cover electrical, mechanical, and the software
Yes.
interface.
Yeah.
Because my guess is they could develop something great, but if they don't know how it interfaces with what you're doing.
Yes.
So
So that's why the team organization, one of them will be integration and validation. They'd be helping on trying to interfacing and communicating with the Lunabotics team of figuring out how we could work well and make both projects a success.
but the interface ideas that we would define the information that's passed
Yes.
between your device and their
The
device.
device, yes. So yeah, we that'll be I guess when the senior design starts, then we'll. Right now, Dr. Kuklev has not really started much on senior design, so we just got our teams recently.
And Beef knows the system boundary.
Yeah, I mean, we still have a draft of it, but whatever is on the draft was the system architecture, which we showed a couple minutes back.
And NASA would call it an ICD or interface control or interface interlock.
I mean, we do have to submit a systems engineering paper as a part of our final project. So most likely before that we will finish, we will work on a detailed system.
You guys could tell me what you would like to use in 12 steps, what would be useful?
I am planning to implement all those 12 steps.
Okay.
Yeah.
Very good.
Yeah. Because I really like the approach. It's just that not everyone knows the like how we proceed with it, so it just takes a bit of time to explain everyone like how every step works. That's what happened yesterday. Like we were working on the
Okay.
thing, and then everyone was confused how that the all the 12 first three steps work. So for a PDR, we were doing first three steps, and for the CDR, we were going first six steps. For 3 steps for PDR, and CDR was first 6 steps.
And by the way, this whole 12-step design is meant to simplify and eliminate I gotcha mistakes and issues. So, you know, as you guys try it and use it, I'd like your feedback.
Sure.
And the other thing I'm learning teaching senior design is that building a test stand early, you know, because a lot of these things, we really don't know exactly how, like, the Jetson works and mechanical. And so maybe we could think about setting up some sort of arena, finding a space for the test stand. So you're welcome to use the lab that we've started on over in, we call it the Triple E, Entrepreneurship and Enterprise Engineering. That's where the 3D printers are and also this PCB printer. But we really probably need to set up the actual test environment.
Yeah.
And
We just don't know where we can do it and how.
but what I would recommend that you guys do is create a bill of material
Sure. Yeah.
on all the tools you think you need. That would be very helpful. And I would recommend building a scale model, actual size
Arena.
arena.
Okay.
And we could at least.
I mean, if we do that, then the
Then we have to find space.
topic which I mentioned yesterday, like continuing this as a senior design for fall through spring semesters, I think it will be helpful for all projects which are coming up.
But if I had a list, I might be able to help you guys find a spot.
Yes. Yeah.
The dirt proposes, and even think about a dirt that's close, that's lower cost,
Sure.
a material.
Yeah.
I'm sure we can find something that
There
Very
is
closely related.
there is some basalt thing that is
Which
like
the
super
main
fine.
campus did.
No, they got the BP one.
No, before
Yeah, they got BP.
BP1.
Oh wait, oh yeah, they got the.
They had something, I
Yeah, there was
forgot
an
what they
iPad.
mentioned. So we did a tour to the main campus, and we met their team and saw.
they've
their
been doing this
entire-
project for like 12.
Yeah, like very
years.
long time, more than 7 years.
Which department?
So how
Engineering.
no, it's under engineering. It's a Apex project and a VIP project. too.
VIP project too.
Yeah. So VIP is usually technically under EC. VIP is just a method of having students be able to do research and or big size projects while outside of class essentially, but still having it be a class. So
I mean, what they mentioned, they started as a senior design team, like senior design project, and then they converted this into a club, and then it just moves forward together. That's what we are doing, but we did the opposite way. We formed a club, and then now this is coming as a senior design
But
project.
that's in their ECE.
Yeah.
yes.
So we can.
Yeah, usually UWB system, just one of these boards is about $200. The fact that we could get something with only 0.2 like second communication time is for $80 is unbelievable. We need 5 of these, so it's gonna come out to 400. So originally we were thinking about about 600, but 400 is really cheap.
Why are 5 needed?
Yeah, 5 are needed.
Why?
So as seen in the last slide, for triangulation, we need 3
All this.
anchors and then 2 tags. All of these are
Oh,
transceivers.
each of those are an Arduino.
Yes,
Oh,
yes. Since these are all transceivers, So they transmit and receive. So because that's how we're gonna do the synchronicity calculation. So yeah, that's why we need 5 of them. Yeah.
So the main brain or the powerhouse of our robot is the Jetson. We got a Jetson Orin Nano priced at $250 to $49, which was sponsored to us by EC department. Like it has an onboard CPU plus GPU system, which which will help in like processing all the complex algorithms for navigation, like real-time LiDAR and RGBD processing. Since it's a GPU, it will enable a parallel numerical workload because CPU does not provide a parallel computing method, but the GPU is more effective in that. The Jetson introduces is or connects to a new like a new concept or like new thing which we're going to talk about is the robot OS. The sensors are interfaced through the robot OS 2 driver nodes running on Jetson, and the driver nodes are basically the LiDAR, the IMU, the encoders. IMU and encoders are still a part of signal design, but majorly the driver nodes are connected like through the sensors. The ROS2 is basically the coordinating system between the sensors and the main algorithm, which is responsible for AI and object detection. The perception and AI nodes execute on the Orange GPU while navigation mission nodes execute on the CPU. This is just so that we don't overload the GPU altogether with everything. It's a very simple pipeline. The sensors go to ROS2. ROS2 is responsible for perception and AI, and that decides the navigation and control. So what is ROS? Why are we mentioning it too much? ROS is something which is ROS is Robot OS, which is a standard used by almost everyone in the industry for robotic applications. It provides a very modular and node-based architecture for perception, navigation, and mission software. It's simple to implement, but since we are dealing with some complex navigation algorithms, it will require high power and high usage on the CPU. So the ROS will lower down that if we directly hard code everything into the GPU. And this is like the other just the basic information on how the ROS is going to help with AI and perception, because the CS team will take over for the ROS part. Robot OS. Deep.
Just press it.
Just HDMI. Don't touch the mouse.
IMG was a dead record.
So this is the software part. So we are targeting 3.5 autonomy level, which consists of mainly 4 parts. The first is the mission backbone, which is set out in a specific sequence, which I'll talk about later. It's basically all the tasks you have to perform from navigating to excavation, deposition. The second one is the reactive safety and recovery fallbacks, which is basically if something goes wrong or the robot stops responding, we have to have a safety mechanism, which will then lead to from autonomy to semi-autonomy or even manual if needed. The third one is 2D navigation and planning, which is the path planning and localization algorithm, which we will need for the robot to move and move to the deposition berm and also the excavation zones. And the fourth part is the 3D hazard handling, which is the rocks and crater keep out, which is basically when navigating there might be rocks or craters which we have to avoid with a specific amount of, we have to keep a buffer in mind for that too. And why are we targeting this autonomy level? It's basically because as we talked about previously, that it has the most amount of points in the competition, 600 points for full autonomy. And if we get that, then we have a very great chance of winning the competition. And what we have right now is the software team has already set up the ROS and have a gazebo ready with the lunar terrain environment, which we will show in a screenshot later in the slides. And we have a specific perception plan and a navigation plan ready based on our research of what is feasible.
This shows our robot system architecture. It uses a modular pipeline approach. For sensors, we use the 3D LiDAR and RGB. We use it for vision and IMU and encoders for localization. For perception, the raw data is converted into like actionable form. And for navigation and mission, nav2 is used for planning and controlling. And the behavior tree is used for recovery. And this shows like modules how ROS interacts with each other.
So for the perception, these are the three main objects you have to keep in mind. The rocks, the craters are the like depressions, and the berm rods are the rods surrounding the berm, which we have to keep in mind for the deposition zone. Yeah.
So the output, for example, CND underscore, is that already code that's written
For
the library? Yeah.
this one? No, this is the, I'll talk about it in the next slide where we, for a schedule, but we have done these two. Where we have our simulation environment ready with the lunar terrain and the rocks and craters. And we have to now make this navigation algorithm where we can navigate the robot in the simulation.
I think what you were asking was like those are the nodes which you have
No, you
mentioned.
said the code is written.
Yeah,
He's
the
asking
outputs.
if these are the outputs that.
Oh, yeah, the command velocity is the output you will give to the mechanical parts for the robot to move. So that, like I spoke about earlier, that the velocity might differ based on the weight of the sand we pick up, because we have to keep in mind the, what do we call, to for the robot not to disbalance, or like it's not being able to move if we pick up too much. So like we have to defer the velocity. So we will output this every time when we like autonomous, like in real time dynamically, so that it moves accordingly in the same in specific velocity. So this is a behavior tree. When we start, it always checks the safety gate if the robot is like what is the environment right now, if the robot is near a rock or crater, and it also has a e-stop button, which the electrical team will electrical team will integrate. Yeah. And then we have the mission sequence ready. This is basically the steps we have to follow, and it will repeat until the time we are doing the excavation and deposition. The first is the initialization and localization, that where the robot is at the starting. The second is the navigation to the excavation zone. Third is the excavation cycle where we excavate. The fourth is the navigation to the constructions, like how we navigate to the deposition zone, and then we dump it. So, and this will repeat until we have the 30 minutes timer. And so basically all these steps are monitored by the software teams, because it has to work autonomously without any, yeah. So it has to work autonomously without any intervention from the mission control group. And no option is coming here.
Well, it's on the. It's been extended.
Oh, okay. Did I click it?
It's pretty good. You can 2 hours. So on the right side,
Yeah.
this is a breakdown of the
Steps.
modules.
Yeah, it's the behavior tree which the system will follow every time it starts. Right.
Behavior tree, but that's implemented in software, right?
Yeah, yeah.
Okay.
And we have the sequence nodes, which basically runs continuously until a child fails, and these are the fallback nodes, which is a alternative node which will keep checking if the sequence nodes are failing or not. And if it's failing, then it will run until one succeeds. Like if it fails, then it runs. So, and then how we using it? That mission, the skeleton is fixed and it is repeatable. It keeps repeating, and we make some adaptation. Like we adapt via the parameters, basically the weight of the sand, the speed, the clearance of the objects nearby, and we have safety gates, which I spoke about, the e-stop button or the perception algorithms. And the recovery is explicit, like we have this semi-autonomy or the manual modes also.
Again, one more question.
Yeah.
So for example, dump cycle
Yeah.
is a software module.
Yeah, because we have to tell the robot when to dump when it has reached the dumping zone.
So can I just give a comment back to that?
Yeah.
So this is like a use case for software.
Yeah.
Yeah.
Oh, do you want us to add as another use case?
Well, no, I just think it's a nice, straightforward way to see operations.
Okay.
Yeah, we have to plan.
Very my systems have.
We could also write a like a very large nested if else logic, but it would be very tedious and it would take much time to.
I'm saying this is good.
Yeah, yeah,
I like it.
yeah. That's why we chose behavior trees.
But so in electrical and mechanical engineering, we're less rigorous than computer science.
Yeah.
Okay, so that's my comment to you guys is the more we can break down how these mechanical and electrical systems work like software, I think the easier it is to understand.
I think the system boundary diagram which you were mentioning, that will clear it out.
And that's what we would also call a use case.
Yeah.
So I borrowed a lot of design ideas
Yeah.
for systems engineering from computer science.
Yeah.
That's one of them. Anyway, great.
So we have three perception nodes: rocks, craters, and berm docking. So for rocks, the 3D LiDAR detects that and detects the data. We get the data from the LiDAR, and we remove the unnecessary data using clustering, and then we mark it as an obstacle for the robot to know. For craters, we detect the height of the crater, and then it's kept as a no zone. Like, don't go and dip yourself in the crater, or else you'll get stuck. And the berm docking happens in two stages. The stage one is navigating. It first nav2 allows us to navigate till the berm docking, and then using the camera we detect the 4 poles, and then we deposit the.
So for the rocks, it is above the ground, so it is easier to detect because we can see it with a depth camera also. So the voxel layer is basically it converting the 3D data into 2D data, and it's easier to detect. But the craters are a tedious task because it's under like it's depression in the ground, and it might detect as the ground is uneven. So I'll talk about how we detect craters in the next slide in detail. So this is the crater handling, which is the negative obstacles. So what we do is we take the data from the LiDAR, the 3D data, and we basically reverse it. So the depressions also look like rocks because the negative obstacles also become like positive obstacles. We basically reverse the 3D point cloud data 180 degrees so that the depressions also become above the ground, and we can see the ground segmentation. And the elevation grid, which I was talking about right now, we do it in a grid resolution of 0.08 meter, which is 8 centimeter, and we detect the depressions, and we have the inflation radius of 0.30 meters, which is 30 centimeters. For this is a buffer zone which we have to keep in mind so that because the craters are a very big problem because the robot can get stuck and it won't move then, no matter what we do. And this is the keep out map that the cost maps will mark it as a lethal zone that don't like go even in 30 centimeter radius of craters. So the crater, this is our method for detecting craters, and yeah.
So this initial tuning, what software did you use to simulate this?
We are doing it in a Ubuntu virtual machine, and we have downloaded the ROS structure in it, and we have also downloaded the gazebo mechanisms where we can simulate it. I can show a screenshot later in the slides that will
So
come.
you have both of them. So you're saying you have a mechanical simulation to get those parameters?
Yeah, in Gazebo there are simulations which we run. It's a virtual environment which we run, and then we run the Gazebo according to our needs. We can create craters of whatever size we want, whatever width we want, and also rocks, whatever size we want.
And gazebo is what?
It's a software in the Ubuntu virtual machine.
That's a simulation software.
Yeah.
So you can create the arena and simulate the bot, basically moving using the navigation and perception code that we have written.
I would like to see this.
Yeah,
Yeah.
we have a
I'm very
screenshot.
impressed that you already know your grid resolution.
Yeah, we have a screenshot later.
So that's 80 centimeter.
8 centimeters.
What,
Yeah,
so
it might change by a little bit here and there, but this is what we have planned for right now when we are doing the
oh,
ROS.
so it's 8 centimeters.
Yeah.
resolution.
So we use Snap2 because it's stable path and easy to tune, but so we're using LiDAR-based 2D mapping, and we're using 3D LiDARs for detecting hazards and like berm docking. So what happens if the robot randomly like starts moving or is lost? So what we do is when it starts, there's a short scan routine. It spins around and checks its surroundings, and it settles localization. Then it drives to a waypoint, and then it rechecks its environment and starts moving. So the like behavior tree never lets the robot takes risky decisions until it gets an okay from perception.
And for localization, we also have the UWB, which Akshat spoke about previously, which is we can use it as an alternative if we want the data from UWB also as a localization. We have it integrated in our software code that we can also take the data from UWB workspace.
You've been working on this for how many years?
1 month. Yeah. So we are following layer by layer cost map functionality, where we are basically creating an inflation layer, which is the clearance buffer for the rocks and craters, and we detect it and we convert the 3D data into the 2D images for the ROS to understand it and make decisions. And we also have a static map layer which is given to us by NASA so that we have the navigation path already, which can differ once we have the environment. And the path planning, we already have a global planner which will route through free space without any obstacles. And we have and when the local planner kicks in, it will track the path in real time. Like every time it navigates, it will make a decision that okay, this path is shorter, so we can take this path and it will save time. This will run dynamically. And if we are also the safety mechanism, if we are blocked by a rock and crater, like on all, like almost not all sides, but like on in 180 degrees circumference, where we can just stop and scan our environment and then replan our course according to the environment. So it can do that. It's basically a safety mechanism for the path planning. And why are we using cost maps? Because we don't know where the obstacles and craters will be in the pit. NASA has given us basically a basic idea of how many rocks and craters will be there, but we have to adapt to the environment, and we have when they can put the robot in any direction at the starting of the competition. So we have to that's why integrate not hard-coded navigation routine, but cost maps which can detect the obstacle zones.
So there will be rocks.
Yeah,
Yeah,
Okay.
they'll place rocks specifically
Wonderful.
there too.
and we don't know where they will place it and what direction they will place the robot also at the starting. So it could be in any direction. So this is the workflow. Basically, we have set up the virtual machine and the gazebo. The navigation app 2 is which is the simulation, and we have detected the hazard. Like the third part is detecting the hazard, the rocks and craters, and the fourth is the mission behavior tree, which is a sequence and recovery. And after we have completed this on the ROS framework, the Ubuntu virtual machine, then we will get the Jetson, which we will flash through SD card, and we will run it on the Jetson. The sixth step is test what we have written, the code of everything
integrating the hardware from the mechanical team and electrical team. And when we test it on the any sandpit or something, we have the field tuning, which we will then alter the hyperparameters so that it navigates to the best path and it detects obstacles and craters without any loss in time. And this is in compilation with the competition playbook, and we also might have posts and logs. So yeah.
So this is our plan until the CDR. We're currently done with week 1 and week 2, where we set up the virtual simulation, and we're working on week 3, which is building an obstacles alone world. And then by CDR, we are planning to finish everything and have a polished architecture into place and on.
Yeah, so we are right now in week 3 where we are making the navigation algorithm, and fourth week we will make the algorithm for the detecting all the rocks and craters and using the cost map, and the fifth week will be traversing through the behavior tree which I showed earlier, all the steps of the mission plan, which is basically where to navigate, where to traverse, the dumping, excavation zone, how to navigate through that, and return and repeat all the steps from starting, which I showed earlier. And this is the week 6, which is the PDR, which we will have everything ready by then.
So this is simulated.
Yeah.
Okay.
And this is the screenshot of what we were working on or in the virtual environment. We have basically many terminals running side by side where we get the data and we basically these are obstacles, and this is the robot where we can create obstacles and craters according to the size we want. And this is based on the lunar terrain. So you can see that this is the gazebo version. And these are many terminals. There are many more terminals running in the background where we can get different types of data, the camera data, the LiDAR data, and we can output the linear velocity and the angular velocity accordingly.
So I'm going to ask all of you the hard question. How do you know that the simulated performance will work with the actual build?
We can basically.
You don't have to answer it fast. It's not a fast answer. In other words, there's 3 different disciplines here, maybe 4, if you count systems engineering. But how do you guys as a team work together to ensure, this is awesome,
Yeah.
but how do we ensure that the mechanical electrical build, the device, is going to perform well? Do you guys have like a process or a method for getting everyone on the same page to test it?
So the testing will start only when we have hard components in place, like we have actual components
I
with us.
understand.
And more importantly, if the simulations are working, it just gives us an assurance that, okay, now we should start working on the hardware, because if the simulation itself is failing, then moving forward with buying anything and then working on it and then later figuring out that, okay, it doesn't work, doesn't make sense. Especially when we are on a budget crunch and we really don't have an assurance that, okay, we might not be able to get like what we are asking for.
I hear you.
So,
And I'm not trying to make you guys feel defensive here.
no.
Is there any piece of this that you could, build a physical prototype and concurrently or work with the software side to see if it works?
So right now we
Maybe
gave them a Jetson board so that they could start testing this on the Jetson board.
Yeah.
But simultaneously, once we have other components, like we are ordering the camera, we have the Raspberry Pi, not Raspberry Pi, the RPI LiDAR.
We have the sensor.
We have the sensors and everything. So once we have other, like every electrical component in place, that's when we can do an indoor testing or like in-house testing of if the simulations which are provided by software team actually provide the similar or like near to same results in the hardware side as well.
See, what I really liked was here's what we're doing week by week to get to CER.
Yeah.
What I would, suggest is that, you have a week by week, plan that would say, here's what we think we can test.
Oh, okay.
You know, just setting the expectation, and maybe it's something really simple.
Yeah.
But, you know, in week 1, we're gonna do this test, and it corresponds.
I thought that was step 7 and 8, the testing plan and validation plan. So,
It is, I think but the idea is to test modules.
okay,
That might be one thing I would suggest we
start
put in
doing
the
it.
12
Okay,
steps
okay.
as well, is to think about modular testing as opposed to the
Full testing.
full device. And, but I think you guys are doing an awesome job. It's
Yeah,
really
the
great.
best the software team can do is recreate the environment given by NASA, and like
Yeah,
that the robot works, it can detect obstacles, it can navigate through its path from point A to point B,
yeah,
and it can find the shortest path. And once we get the components and we integrate the robot, we will test it with the robot. Of course, we have to change something will go wrong, of course, because we are doing it for the first time, and we
Yeah.
will change our parameters
but
based
if
on.
you could go back to that next slide, that prior slide. This is what I would suggest for the mechanical and electrical teams, is, and have one more that says what we plan to test, and think we can test. And it could be really simple. I test that I can plug in. Okay. But all of that hardware stuff, physical stuff, always takes, my experience, 3 times what you think it will take.
Yeah, that's true.
Yeah. As a minimum.
Something will go wrong for sure.
Yeah.
So, but I love how
Yeah.
concise that was, and so CDR is only 6 weeks into February?
No,
Yeah.
4 weeks.
4 weeks. from
We are
now.
already done with 2 weeks.
Oh,
4 weeks are
yeah.
oh my.
Actually, we are 3 months behind schedule, so our
Okay.
review sessions are placed very close to each other.
Okay, but that might help get back on schedule.
Yeah.
We're on it tight.
At least our CDR is when it was supposed to be planned, so after that everything should be on track. We will start building next week onwards.
Yeah, and I understand you need a test stand or test
Yeah.
platform, so maybe we'll work with you guys on that.
Sure.
Yeah.
And so this was the gazebo software.
Yeah, it is not very. We will add some point A to point, like this is the excavation zone, this is the deposition zone. We'll add craters here, and so that it can navigate through its path and we can do it in the best path possible, like the shortest path possible. And we can change obstacles in that and see that it can adapt to the environment. So we will basically run simulations throughout these 2-3 weeks, and we will add things like now different algorithms and test which works best.
Like the Jetson part processing, is this simulating what the Jetson does?
Yeah, we once we are confident with this, we will test it on Jetson also. We will flash it using a SD card, and we will have it on that because in the real NASA where we will test it in May, we will have the Jetson on which we will running it. So it shouldn't heat up much, and we shouldn't take much of the computational power. So we have to test all those things also to optimize the code.
Is this software something your department has, or? the
No,
testing
so this is
agency?
a software virtual environment which we are doing it in the ETCS lab, this room,
Yeah.
and because we can't do it on our Macs, it is not compatible with MacBook. That's why, yeah. So we are using ETCS lab computers.
But is this owned by the university?
No, it's available. Anyone can download it on
Open source.
open source. Yeah.
So
The budget.
budget, the main
Okay.
part of the project is budget. Our proposed budget during the SDR was $9,000 for the robot build and around $9,000 for travel and travel sponsorship. So right now we have a committed sponsorship of $3,000, 500 from ECE department, 500 from CS department, 1,000 from Dean's sponsorship, and 1,000 from Phil Wright. So
we have $3,000, and I coordinated with John only for getting a Phil Wright sponsorship for the project. So out of that, right now we stand at a $722 because we ordered a battery pack and BMS through my own honor scholarship. Then Jetson Orin Nano was through ECE scholarship. Then we got a Cloud Pro subscription so that this ECS team can like improve their code more efficiently, which was through Dean sponsorship. Google Collab also required to test everything, which is also through Dean sponsorship. And for a custom domain called PurdueFW Lunabotics.info, which is like a year-long subscription, also through Dean sponsorship. So we stand at a $722. Out of 3,000, we have remaining 2,278, and we are expecting to exhaust all of it by end of next 2 weeks, because every electrical component which we mentioned, if we just start placing orders for everything, we will exhaust everything for electrical and software side, because more subscriptions and more services will come into picture. It's just that because of this, the mechanical team gets kind of neglected because we currently don't have a short sponsor who will give us money for mechanical machining, parts, and other things.
So, but right now it looks like for the mechanical side of things, most of it at least, it's just going to be directly from our budget, which means from the metals down to the machining tools to everything.
Everything, like basic from starting to choose which material to manufacturing and machining, everything, we don't have any budget, short budget assurance right now. So
Do you have an estimate of the cost?
around $6,000 is what we had initially proposed.
I think what that's like if we need the most amount of money for every component, I think realistically, I think it should be like around 2,000 to 2,000.
No.
Worst case.
If you're including motors, then no.
Yeah, with that's excluding the motor.
Yeah.
Just for the metal.
Motor sponsor, though. Somebody makes some.
We can find motor sponsors, but like, so since we were running short on funds, we had to cut down travel funding also. So we were proposing a $9,000 travel fund for 20 people. Now we are proposing a $6,600 travel fund for only 12 people.
Where would they travel to?
We have to go to Florida in May. So our commencement is 13th of May, and 14th of May we have to report in Florida for the competition.
So you have to fly.
Yeah.
A few of us will have to fly, and then the robot has to be driven there.
Driven.
So someone has to be the.
So a couple of students will go by road
with the robot
in a van.
Of course, if it were March, it would not be.
But so we asked, so Dr. Chow Chen gave us a contact for Bosch. She said Bosch will help in not manufacturing, mechanical sponsorship. I have reached out to Purdue IT because since I'm an employee, and they referred me to a research computing center, RCAC, in Purdue main campus, who is also willing to consider our request. Carlos is talking to Franklin Electric to get them on board as well, since Phil Wright is already here. And I contacted the vice chancellor just so that to see if she's interested, and she's also interested in providing us relevant funding. We proposed $7,000 to her, considering travel and robot, but our main priority right now is robot, because travel, it can be compromised for the robot, but robot cannot be compromised.
Which vice chancellor?
Christina Surface.
Okay. Do you have like a total list of everything?
We should have it by Monday, yes. Because after today, tonight we will have a meeting, probably tomorrow we will have a meeting, and in that our idea is to finalize the second last budget, like second last stage of the budget. Like we are on, this is the third stage. We have total 5 stages, so 4th stage of budget would be 90% of all the materials covered, and the last stage would be 100% of all the materials covered. So we should have that list with everything by Monday or Tuesday latest. Yeah.
Who's online?
Dr. Guping Wong was emailing me questions. So he's online. Dr. Antien Wong is online.
Oh,
And I think Dr. Liu also said she would be online too. It shows 3 viewers, right? Yeah.
so they can see,
Yeah.
but we can't hear them.
Yeah, we can.
Okay.
I think Dr. Wong.
I asked them to drop like questions in the chat.
Oh, okay. But Dr. Wong sent me an email, so we have this question. Again, a special thanks to Dr. Liu, who's our faculty advisor, Dr. Sharif Al-Fayoumi, who's the Dean of College and one of our official sponsors, Dr. Guping Wong, Chair of EC Department, who's also our official sponsor, Dr. Adolfo Coronado, who's the Chair of CS Department, who's also our sponsor, John Haverstock from Philwright, who is also our sponsor, Dr. Antien Wong, Dr. Elizabeth Thompson, who are EC faculty and who have provided us a lot of feedback for our initial reviews, and to you, Dr. David Cochran and Joe Smith, for providing us with the 3D printing facility and allowing us to use the Lucidchart setup, and Jason Moyer for helping us with the initial 3D prints which we use right now. Yep. Thank you.
Thank you for inviting me.
No problem. Yeah. So,
when is the next meeting?
we have the PDR on 27th of February.
Okay.
So 4 weeks after this, which is also Friday, if I'm not wrong, or Monday. Yeah.
Will you send me an invitation?
Yes, I will definitely.
So the next steps might be to look at a test facility.
Yeah.
Why to see all this work. Thank you for inviting me with it. Yeah, I think the Lucid chart, that's really kind of a system design approach. And I think it's great that you've embraced
Yeah.
that. I think looking at that test plan, thinking through the different tests, even if you can't get them all done in 4 weeks, what would be involved in the test? Maybe create a timeline.
Is there any possibility under your department for a sponsorship for this, or like if you could connect with us? I was thinking if we could ask Miltech if we don't get the PCB facility on campus on time.
When do you need it?
PCB. Yeah.
Well, we put the order in on Monday. They told us, I would say probably in a week or 2.
Okay.
So yeah, certainly we could help with that, the 3D printing. Tools, I'd like to know what tools you need,
Okay.
and again, discussing where we might do the testing.
Sure. I mean, we have ET120, but like that's a very short space. I don't think so we'll be able to build our entire robot in that room.
Can you show me?
Sure.
I don't know.
Oh, do you have the keys?
No, we'll have to go upstairs.
You want me to get it?
Yeah, I'll just close
I'll
this.
get the keys.
Is yeah, are there any questions? Like, are there any viewers on the thing?
Yeah, this is what, no.
No questions. Okay.
Thank you.
Thank you, Dr. Cochran.
Feel free to be up to speed when you give me updates.
Yes, definitely.
You guys can email me. I can always do online too.
Okay. Yeah, sounds good. Thank you for
So
attending.
you were going to show me 120 real quick?
Yeah, he's getting the keys. I'm just
Have to.
finishing the live stream.